And then I've been focusing on only one small story. Okay? So for a long time in my group, we've been very much interested into natural product synthesis. And the way we deal with natural product synthesis is finding new ways, shorter ways, inventing new methods so that we can tackle synthetic problem. I would say real synthetic problem applied to natural products. Sometimes it fails, but sometimes we're lucky. Not so many times, but we can be lucky. And we can make quite a variety of these two. So for instance, I can make a small focus of a program dedicated to alkaloids, polyhydroxylated alkaloids. And the main point of this was to use ring-closing metathesis, but with enol ethers, so that we can install completely and selectively the polyol moieties. Then we've indeed been interesting, and that was a long while ago, but I love this small natural product called kainic acid, and we use high pressure disalder because this dienophile is very reluctant to normal disalder condition, sterically crowded, so you need to put high pressure so that we can get the product in the end. More recently, and I've been now working luckily with talented colleagues, and for instance, all that work I've been doing with Dr. Sébastien Carré, he's an assistant professor in Grenoble with me, and we've been dealing with the synthesis of these licorine-type alkaloids. And we've been able to make a few of them and developing methods. This story would be too long. I've been told I've got an hour and a half, so it would be too long, so now for 20 minutes. So, but we've been developing thioimidates in order to install selectively after chiral centers, and then we can reduce them to imines, and this leads to alkaloids, and also other methods developed on the way. And also recently, we've been working in catalysis, asymmetric catalysis, and all of that is related to also the work of Dr. Benjamin Dars, and he's a CNRS researcher. And he loves to work with highly reactive carbene precursors and rhodium asymmetric catalysis. And for instance, we've been able to make these 7 member rings in high enantiomeric excess from very flat and simple substrates. Also, we've been developing other catalyzed reaction, and recently we've been looking to high valent sulfur, sulfur 4, sulfur 6 derivatives, and especially those that are not really well known. This was one of the first examples of the synthesis of these sulfinamidines, and as you can see, they look simple, but there was a few months before Willis published the same thing in Willis from Oxford. They look like sulfinamides, and sulfinamides are broadly known and used, and these sulfinamidines are rare. So now we are engaging a program to study a bit more of these rare sulfur 4 and sulfur 6 derivatives. Okay, and aside from that, natural product methods, sometime we tend to go a bit in biology, but not alone, because I'm not a biologist. I am a synthetic chemist, so I go and collaborate with people who have that talent and that methods. So for instance, I have colleagues that are working on finding inhibitors on E motif on DNA. These are very particular motifs of DNA that could be targeted for curing many diseases, as you may think, cancer, for instance. But they're looking for inhibitors of that particular one. I've been working with a company, Edelris, and through a European program, we've been looking for helicase inhibitors. And this seems to be a very interesting target, at least for what the biologist told me, and from what I could understand, that there could be unique opportunity for targeting them, and there's only a very few inhibitors. So Edelris is building, a large variety of natural-like products, and we've been collaborating for the design of them. And a bit more remote, but that's something that's maybe the easiest publication of my life, is collaboration with a colleague who is doing DNP analysis, solid-state NMR DNP enhanced analysis. And yes, it was just published this year, and we could only provide N15 enriched amidins in that case. Okay, so today I wanted to focus on this small story. And this story is quite old, and it relies on cation reactivity. Cation are unique species that can do thermal 2+2 reactions. So they are really nice to build cyclobutane, cyclobutene, and maybe analog with particular activities. So we've been working in that field for a long while. And then we got interested in these, omuralide and lactacystine. I think we got interested in these natural products, like many others, in the year 2000, 2010, and because they were very promising proteasome inhibitors. I think there's nothing on the market yet about this kind of structure, but they are part of this lactam class of natural products. So you see salinosporamide A, that's maybe the most famous one. It was a nanogram scale activity, and there's a lot of them. So like many others, we thought, okay, maybe we can try to make the best possible synthesis. We tried at least to be original to what was published before. So we decided to tackle these small products. So it looks like, I would say, maybe ridiculous. It's a 5-member ring, but 1, 2, 3 stereogenic center, 4 with the 1 year. But there's a particular problem here is this quaternary one. And that takes a lot of time, and there are some really nice approach to solve that problem. And it's also, you have this cis fashion substitution in the 5-member ring. And again, it may look ridiculous, but that's also something to tackle. Okay, so how did we want to do that? Well, the initial idea was simple. Take advantage of a diastereoselective 2+2 cycloaddition between A18, we have to define which one we want to use, and a chiral enolither. So this is a chiral auxiliary. Then we should have a 4-member ring, cyclobutanone, and we would use the venerable Beckmann ring expansion, direct access to the lactam, and then we should be able to make a variety of them. So that was the plan, and the plan was based on many reports based on what we've done with dichlorocaine. So dichlorocaine is extremely reactive. That reaction is orbitally controlled, and you need a very electron-deficient cation. You have a very electron-deficient carbon center. With enolither, you have the nucleophilic part, and it's not synchronous, it's a non-synchronous 2+2 reaction. Okay, and based on this, we've been, of course, the chlorine are not very helpful. If I go back to these R2 groups, you need to build here the quaternary center. So you need something that, in the end, will be desymmetrized. So we tried a few, and we escaped from the dichlorocaine. As you can see, its reaction doesn't work with this apparently nice at the beginning ideas. We have these alcohols that we can oxidize in the end to make an acid here to build on the side afterwards. So we had to go to a bit more complex substrate. And the one we really liked were this siloxane derivative. Of course, we had in mind that you can easily or sometimes easily oxidize carbon-silicon bonds, the Tamao or Tamao-Fleming oxidation. So we decided that would be a nice precursor, at least to start with. Okay, so we could do that first reaction. I'm not entering much detail, of course, on the optimization of the reaction condition. With a reactive ketene, the reaction is room temperature. Here you have to have warm a bit. but still you maintain a very high degree of diastereoselectivity. selectivity. We're doing natural products, and of course, well, we need to do a bit of starting material because not everything works. So we need grams of the starting material, and yes, easily you can do that on more than 10 gram scale. Okay, so that's the first point, and maybe the most difficult part started now. Now we have to find a way to the final product over there. Okay, ST, I didn't mention here, is this one, stericol, so it's a benzylic aryl alcohol. So we had first to play around, reduce the ketone, protect the alcohol with the TBS, and then deprotect on the other side. The reason is simple, is if you deprotect here, you have a retroaldol reaction, and we lose the full membrane. So we had to play, and this one now is robust, and we can keep it in mind, in hand. Okay, once we had this one, the next step was a Beckmann. And the Beckmann reaction is a very nice textbook reaction. But then when you want to apply it on a bit more complex substrates, you discover there's the normal Beckmann, the abnormal Beckmann, the one that goes to the nitride, following by the reter-cyclization, and sometimes it does not never cyclize, and you end up with a non-cyclic compound. It took us a bit of a time to optimize that reaction. So we are using mesithylene sulfonyl hydroxylamine, so a pre-activated hydroxylamine that's going to in situ form the oxime and rearrange. And then we protect the lactam, and as you can see, it's very sterically crowded on nitrogen, so it's the oxygen that gets protected as a benzyl protecting group. Okay, so now we can start and play around to desymmetrize. And that's my favorite part of that with the students. How could we find a solution so that we can oxidize one carbon-silicon bond without the other, and try at least to oxidize one of them? So we found the trick. If you deprotect this TBS, and then if you had phenyllithium on it, you have a selective addition of the phenyl group on that silicon, which is seen to the oxygen. And okay, we propose something. We believe, and there are some precedent by Amos Smith on that. So deprotonation, silicon siloxane opening, and then the phenyl groups can come back on this one, because this one is already charged with the oxygen. So there we are, we can desymmetrize, and we have one silicon group with a phenyl, one other with an OH. And now we can play around with the Tamao and Tamao-Fleming oxidation. One of them will selectively oxidize the first one, and the phenyl group needs to be activated before oxidation. Okay, there we go. Under this condition, we can selectively oxidize the first one, and then the rest is quite straightforward. Oxidation, isopropyl lithium addition, oxidation, protection of the diol, and then we have to deprotect the amide. That's important because we're using this strong activation of the phenyl group to make the CO bond in here. Jones, and then the rest, and we got lactacystine. So that's the beginning of the story I wanted to talk. A natural product synthesis. I'm not writing the global yield, because you know, after the number of steps, it's maybe not so high. It's quite a short one if you compare to others. And at least it uses this siloxane function in a fancy way. And I think we had the talk, and I like fancy chemistry. I think it's important to enjoy doing chemistry because it's nice and funny, and because you fancy transformation also. You also have to need a goal. I'm not saying you should do it for free, but I think it's all the excitement you can bring to students too. Loving the transformation of carbon heteroatom bonds and things like that. Okay, you remember I told you we had problem with this Beckmann. The base yield is 58. It's reasonable, but it's early in the synthesis. So we wonder, okay, all of that to go to the 5-membrane. Can't we just find a way to go directly from some of these to the lactam? So globally, can we use a ketene in a 3+2 reaction? Okay, that's now both a synthetic problem and a synthetic question. Can ketene do 3+2 reaction? And what we want is the carbon-carbon bond of the ketene to react also. We don't want the carbon-oxygen bond to react. So an obvious precursor of this dipole, and it's known and it's being used by colleagues here, is aziridines. You can easily activate aziridines, and in particular, sulfonyl tosyl-derived aziridines. And there's a number of reports. I'm just putting one here. You need strong Lewis acid, sometimes milder one. Everything we tried with Lewis acid led to ketene dimerization. Yes, ketene are nice, but they are so reactive that they can react with themselves. So of course, if you put Lewis acid, you also activate dimerization of it. And finally, we found also this nice example with lithium bromide. Not such a strong Lewis acid, if you think about it. And indeed, that's the first time we opened the product. Okay, so we have the lactam, and as you can see, it's a mixture of the C-C bond formation and the CO bond formation. There's also another trick here, but we don't have the answer why. You can see the phenyl group is not in the same position for some reason. Okay, so we played around optimization, lithium iodide, 98% conversion, and then we have a single product being formed. We have only the lactam in that case. So that's the optimized condition. It's very mild, lithium iodide. You can use it catalytic. 10% is working nicely, and you mix both of them, and you end up with 90% of the lactam. Okay, so as usual, then you test your reaction with different substituents. So as you can see on the top, we use diphenylketene, cycloheptylketene. It's compatible with, well, electron-rich, electron-poor, ortho-substituted one. So I would say basically most aromatics. We can also change a bit that center. Cinnamyl derivative are compatible. Isopropenyl. It's also even working with cyclohexyl derivative, which was for us both nice and a surprise in somehow. And you can also use N-ethyl aziridine, so you don't need to have this tosyl group onto the nitrogen. Okay, if you use non-symmetrical ketene, ethyl and phenyl, for instance, we end up with a single diastereoisomer. And the phenyl group is seen to the other one. So the phenyl group of the ketene is seen to the phenyl group of the aziridine. You can do that reaction on gram scale, no problem. If you have a di-substituted aziridine, it's not easy to find ways to make this aziridine into a pure cis-trans fashion. So we did not struggle a lot. If you do that reaction, only one is reacting. So we get, again, a single diastereoisomer, and we're controlling the 3 stereocenter on the product. I'm using these bonds, which are, rectangular, not triangular. This means it's racemic. Triangular bond is for enantiopure compound, enantioenriched compound, and rectangular bond is for diastero selectivity. Yes, in that case, if we start with an enantioenriched aziridine, no loss, nearly no loss of the chiral information. And we have retention globally of the stereocenter. So I'm not going to detail the mechanism. We use DFT calculation to try to find what was happening. Of course, lithium iodide, I'm sure you can have this idea. This was also an important, very important experiment, because in our view, this means a double inversion mechanism using the iodine. Okay, so that was a point where we could make lactams, 20 example. Something I didn't mention and is you need this isolated ketene. And if you go in this kind of ketene chemistry, go in the experimental part. You will see if they generate it inside or directly use pure. Okay, and we devised at the beginning this synthesis with isolated one. Why? Well, we wanted to avoid salts and all sorts of side products during that generation. It's compatible with a range of aziridine. So now the question, can we extend that to a wider variety of ketene? Okay, and we thought the problem here is stability of ketene. Okay, so if you want to tackle the high reactivity, the stability of it, well, there's not many ways to control it, either to generate them slowly, slow addition, but then we thought maybe that's the opportunity to try to do flow chemistry. Yeah, we thought we can generate directly the ketene and react it with an incoming reactive intermediate of the aziridine. Right, okay, we got funded for that project, and so we engaged in flow chemistry. If you do flow chemistry, you will see that it's fantastic, but there's one point. You need quite a bit of material to make your test. You need a few 100 milligrams and maybe better grams. Because of course you're consuming the product all the time. Yeah, you put your substrate into a solvent and you keep consuming, so having it on low quantity is not easy. And we had a problem with these aziridine synthesis. So this is a very nice one. It's you start from standard N-tosylamine and you react it with this combination, diodomethane, methyl lithium. So you generate in situ the iodo-lithium carbanoid, and then it's reacting with the CN double bond and you're forming the aziridine. This reaction is not reproducible on large scale. And we tried to make it for more than 1 gram, and the yield was 25%. So you can imagine it's better to do the reaction of 200 milligrams because now you have an 80% yield. So that was the beginning of the program, and we had a problem with aziridine synthesis, but because it was a flow program, we thought, okay, can we do that in flow chemistry? Nothing was done really onto the synthesis of aziridines by flow chemistry. There was some report and some nice work, both by Luizzi and Cappe, for the synthesis of epoxides. Epoxides using the same carbanoids, so chloro-lithiocarbanoids or bromo-lithiocarbanoids. Okay, and in their way they were generating this carbene and then reacting with the aldehyde. As you can see, the reaction time is, the residence time is really small. It's not the reaction time, it's the residence time. Also in the second case, you need these cryogenic conditions to generate everything like this. So this is Barbier type condition, this is before generation. So would imines work? Well, in terms of reactivity, we're really good. So if we take the electrophilicity scale, of course, imines are far more reactive than aldehydes. That's according to Meyer scales. Which is nice, but if you generate them like this, would the methyl lithium react first with the imine? So there was this question of how fast would be the halogen metal exchange compared to the addition to the imine. Okay, so we tried. We rapidly found that the mixing condition would be important, and we now believe and surely believe that's the major problem of the batch reaction, mixing. So you can see we played with residence time with a very simple Y mixer, and we had a bit of methyl addition for slow reaction time and nothing for fast reaction time. Okay, so we're just pushing further. And we change to this small mixture, so you can buy a variety of them. This one is much better, and as you can see now, it's really reacting nicely. We could go down to as little 2.3 second residence time. That was the limit. You know, you had a bit of a tube before, nothing behind, so it's globally really the limit of what we can measure. And as you can see, we have only the desired product. Here, as you can see, we have no methyl addition, the one we wanted to avoid. So if I go back to this table, as you can see, with low mixing, we have methyl addition onto the imine. And I guess that the major side product you get for batch reaction. Okay? Something interesting, if you see that table, is the iodine lithium exchange followed by the addition onto the imine takes less than 0.3 seconds. Both are really fast, but one is much, much faster than the other. Okay, and then we play around with the halogen atom. You've seen we've been using the chloro derivative at first. So what we've been comparing here is X being diodo, so an iodo derivative, iodo-bromo and iodo-chloro. I'm accelerating. Okay, so flow, you can have a lot of different experiments. The diodo is the worst one. That's the one that's published. So if you want to do that reaction, you take the bromo or the chloro, you have high yield, and you can do the reaction at room temperature instead of minus 80. Then if you go to chloro, you will end up with the open product. If you take the bromo at room temperature, cyclization, no problem. Okay, and that's where we are. So maybe we've been doing a large scale synthesis, more than 1 gram. All the aziridine are working properly, high yield most of the time. If you take the chloro derivative, you end up with a non-cyclage product if you want. I'm finishing, promise. So I go back to my first story, 2 slides. What we wanted to do is use flow chemistry to make this 3+2 reaction. Yes, it's working with 1 ketene. We can get 62%. Then you can bring more complexity. If you have this acid chloride to generate the ketene mixed with the aziridine, you also have the lactam. And if you want to bring even more complexity, you generate the aziridine repump, and you also have the compound in there. So you can combine everything. Okay, it's no longer scientific, but you may not know where I'm coming from. So Rouen would be here, very north. I'm not from Rouen. I'm close to Lyon. I'm in Grenoble. A rather small city, maybe, 500,000, so that's nothing. But 10% or more are students. So the university is 60,000 students. We had quite a few doctoral students, a lot of international, half of them are not French. A bit of people teaching and working. It's not far from Paris, it's not far from Geneva by plane, it's not far from Lyon, either it's quite close. And yes, we got quite lucky to be fairly well ranked in France as a province university in France. We first after Paris. And it's also known for this round cycle, so you may recognize that. This is the European synchrotron accelerator. I've done nothing on that chemistry. Sometimes I give a bit of an idea, but sometimes the students do themselves, and also my great colleagues Sébastien and Benjamin. The past students, my actual students, we are lucky to have a bit of money, and indeed we have also this IDEX in Grenoble, which is bringing a bit of money for the whole university. Thank you for your patience. Thank you for listening. If you come to Grenoble, be happy to visit, and do not hesitate. I will try, but I'm not sure to have the kind of hospitality you're doing. I'm not sure I can reach that level, but we may our best.
Thank you very much, Professor Poisson. Any questions?
You'd like to go ahead, Vero? Yeah. So yeah, I have a question regarding this aziridine. So if you can take the chiral aziridine, and then did you study that chirality transfer? Oh, that you did already? Oh, okay, sorry, I missed that. Yeah. Yeah.
We have one example because the synthesis of asymmetric synthesis of this aziridine. So this one is easy to do. It comes from the amino alcohol, so amino acids. But we've done the aziridination asymmetric with chiral ligand based on the rhodium chemistry. But the EE is, and it's not rhodium, but the EE are 60%. I have a slide on it. The important thing is we always keep the enantiomeric excess from the starting aziridine to the final compound if we work in THF. If we work in dichloromethane, it goes down.
Yeah, got it, yeah.
So, is there anything chiral sulfinimidine is known?
That's a very good question. There's a paper just appeared at the beginning of this year. It was the first example,
That is,
and we hope to be the second one
and
in the future.
Did someone prepare any imine out of that?
Sorry?
Did someone prepare imine out of the sulfinimidine? Like, sulfonylamine chemistry to a new direction, particularly
Yes. How to? The point is these sulfinamidines. So that's very early here. Yes. Little is known on their reactivity. I don't think they behave like sulfinamides. In terms of how this nitrogen is reacting with electrophile is also a bit surprising if you look at a recent publication. So I think there's two goals. Yes, asymmetric. How can we do that asymmetric? Because we could also go to higher oxidation state in asymmetric fashion, and also stability reactivity studies. So that's why it's interesting. We have different way of doing that.
Okay, thank you.
But good question.
I got one question on your flow part. When you have longer residence time, you introduce the methyl group, but when you have shorter residence time, you do the halogen exchange. But the halogen exchange reaction is probably one of the fastest that you can have. So it's pretty counterintuitive that you can introduce the methyl because it means that you have a reverse exchange.
No.
No?
No. Oh, sorry. I guess luckily because of the poor.
Nucleophilicity, and you displace the equilibrium?
I think locally because of the poor mixing.
Okay.
You form fast the carbene which reacts. But then if there's no more iodo-bromo, the methyl still react with the imine. That's how we explain it.
Okay.
It's, the cartoon you can find about mixing blue, red, reacting. So for me, it's so reactive that it can also react with imines if you don't have enough iodo derivative around. So you consume it first and then you have addition.
Okay, so did you try other mixer, like linear one? So 180 degrees, you introduce?
Yes. We tried a few mixer, but the goal also is not to block it.
Yeah. You get
because
plugging,
we do lithium salt. So lithium iodide is fine in THF, but if you want a robust one, you have to be careful not to. What we've done is we reduce the size inside of the mixer rather than changing the shape. So we reduce, and then we have a better mixing.
Okay, thank you.
With a T shape.
Okay.
I just have a quick question on how much is it known for ICF2 lithium? Is it known, this reagent?
Yes, ICF.
CF2 lithium. So similar like the reagent which you make with the methyl lithium.
fluorine?
Yeah,
Yes, Luigi is done that.
it's known. Okay.
Yes, he's done the.
Because that will lead to the CF2 aziridine, right?
But you need to recyclize. So you will need CF2. Sorry, I didn't listen carefully. Ooh, that would be a very bizarre. The carbene is known to dimerize very fast. The difluorocarbene to be very unstable, if I'm right.
You're making it instable, so that will flow.
Yes, but maybe we should try. You're right. Okay, we are fluorine experts.
The same question. So, do you need to have a CH imine to make the reaction? So, if you have a desubstituted imine, it could work or not?
Then
Yes.
it goes to another problem of synthesis. How do you make easily imines from ketones? Which looks like an easy thing, but if you really want to do N-tosyl imine from ketones or N-boc imine from ketones, it analyzes, so you have the N-amine. So it goes back to how you can control the synthesis of them, in my view. One of the
There is some example. of
there
this
are some.
earlier.
You're right.
Yeah.
There are some examples. I agree. With limited number.
Long live India and France friendship.